we want to talk about photoelectron spectroscopy. Now, besides being large words, this is going to be a fairly basic idea building off of that photoelectric effect. Notice I've got this HV. We could really say that this could be F here. We could say HF, right? So HF. This is going to be a photon source. So this is going to be a light source coming through and striking some sample material here. And when it strikes that sample material, electrons are going to be shot off at an equivalent angle. It's going to be shot off at an equivalent angle here. And they're going to go up into this machine that is going to analyze those electrons. This machine curves the electrons around so that it can get an accurate reading on the actual energy of those electrons. So it gives them right here, it's going to give them a very specific magnetic field so that even if some extra electrons or lower electrons get excited, that field is going to make sure only the right electrons get into that detector, okay? And by doing that, we're actually able to see all of the electrons in relative amounts that an atom might be giving off. So let's consider for a moment just something like, let's say, sodium. What is sodium's electronic configuration? Well, we start with the 1s. We always start with the 1s2, and then we go into the 2s2, and then it's going to have a 2p6, finally a 3s1. That should be all 11 of our electrons there. Now, what is sodium? What's going to be the highest energy level for sodium? What's going to have the most energy of these electrons? In other words, which electron is going to be the most difficult to strip away here? So what we're really asking is which electrons are going to be the most difficult to pull away? Well, the electrons that are the closest to the nucleus, right? So if we remember Coulomb's law, F equals K, Q1, Q2 over R squared. Well, Coulomb's law says that the closer my electrons are, so this 1s2 is going to be my closest, the lower this radius is going to be, and thus the more force I'm going to have. So these are going to have the biggest force, where these out here, this 3s1, it's going to have a very tiny force. And so it's going to be a lot easier to strip these 3s1 electrons away than it is the 1s2. So when I hit this sodium with a beam of photons, when I hit it with a photon beam, then these 3s1 electrons are going to start to be stripped away at lower energy levels. And so I can have my energy analyzer make sure that I'm tracking this energy level and start to sweep upwards through energy levels and see, I get a peak of 3s1, I get a peak of 2p6, I get a peak of 2s2, until I get to my peak of 1s2. Now, what does it actually look like? What is this analyzer actually going to show us? Well, it's going to put all of these into a graph. And so a photoelectron spectrum looks like this. I've got carbon here. I've got a photoelectron spectrum for carbon here. And notice, on the bottom of this, I have megajoules per mole. This is going to be my energy. And there are a few different ways we measure the energy of one of these. First off, we might be using joules. Often we'll use megajoules per mole because per mole is going to take a lot of joules. Megajoules would be 1,000,000 joules. Another possible option you might see is EV, electron volts. This is a very small unit of energy. But regardless, this bottom portion is just going to have energy going from our largest value to our smallest value. And this is often going to be a logarithmic scale. That means it's not going to go down by 1s and 2s and 3s or by 10s. It's going to go down by divide by 10, divide by 10, divide by 10, divide by 10. So these are not spaced evenly necessarily. But the reason we start with our highest energy here is because that's going to be our smallest shell. That's going to be our 1s2. And we usually write our electronic configurations from left to right. And so we put these largest numbers on the left side so that we can write from left to right. And so for carbon, our highest energy, this 28.6 megajoules per mole, that's going to be my 1s2. Then my next energy level is just going to be my next electron orbitals. It's going to be my 2s2. After that, I'm going to get my last one, which is going to be 2p6. Now notice, on my left side, I've got number of electrons here. This is going to be relative. This machine can't actually detect, it can't detect a single electron at a time, but what it can detect is about how much energy is it seeing. And then about how many electrons is it seeing. And then here, it would do the same thing. And so when it sees this third layer, it sees that it's at the same amount as the first two. And so we, when we look at these graphs, are able to interpret them and recognize that that would be my 2p, oh, that should have been a 6, my 2p2. Should be a 2p2. So let's look at the next one. The next one is an unknown element. And so this unknown element, what is this going to be? Well, I'm going to start over on my left side, see that that's going to be my highest energy level. It's going to be 40 megajoules per mole. That's going to be my 1s2. Following that, my next spike is just going to be the next in a row, 2s2. And my third spike, my third and final spike, well, that has to come after 2s. What comes after 2s? 2p. And how many electrons is that going to be? Well, that's going to be 1, 2, 1, 2. Okay, so then this is about 1, 2, 3. You see that? So this was my 1, this is my 2. I know this because this has to be the 1s2. This has to be. It doesn't have another option. And then when I look at my 2p, I see that it is about 150% the height. So I can see that this is going to be 2p3. So this should be nitrogen. All right, let's look at one more. Okay. This one, once again, at 151 megajoules per mole, this is going to be my 1s2. Following that is going to be my 2s2. My next one, as I go down, as I go from left to right, the only one that's going to not be filled all the way is going to be my last one. And so right here, this guy, this spike, is going to be 2p6, right? So this is going to be 2p6. I know it's going to be 2p6 because it's going to be full. And then after 2p comes 3s, 3s2. And then this is going to be my last one. This is going to be 3p. And I see that it's half the height of that 3s. So that's going to be 1, 3p1. So what atom is this going to be? It's going to be aluminum. So that's how we read a photoelectron spectrum. So we should be able to practice that